Hi folks, welcome to our review session for Calculus 1. The midterm, we're going to be covering limits, how to deal with graphs and limits, derivatives, tangent line equations, how to get those equations, continuity, intermediate value theorem, implicit differentiation, and things of that sort. So if you're interested in those sort of topics coming up for the midterm, we're going to touch on all of them tonight. So if you have any questions along the way, there's a chat box over on the right hand side, so please feel free to use that. Otherwise, without further ado, I'm going to get started. So we have evaluate the following limits for the function f of x given in the graph on the left. So our graph here, we have f of x, and we want to start with the limit as x approaches -2 of f of x. So notice -2 is right here, and the concept of a limit, as we approach -2, we're going to approach it from this side, and so our left-hand side along with our right-hand side. But where we want to do that is the graph. So we're approaching it from the left-hand side here, and then from the right-hand side here. And notice in both cases we're getting the same y value popping out, and that y value happens to be 2. And so even though our function value is a little bit below at this point right here that we just shaded in, our function is actually approaching as we get closer and closer to -2, x equals -2, the function value is getting closer and closer to y equals 2. And so that is our answer. When we're talking limits, we're talking about where is the function approaching, not actually the function value, but where it's approaching. So in a similar approach, we have to find -5. So notice -5 would be right over here is when x equals -5. And we want to be on the function, but this plus symbol right there, that means from the right. So we're going to be on this side of -5, and so we got to get to the function. So the function's up here, and so we're approaching this direction, and we need to find the corresponding y value. And if I can draw a straight line here, right there. So notice we go 1, 2, 3, 4, 5. So limit as x approaches -5 from the right, that equals +5. And on the other side of things, when you see this minus sign appear up there, that's a one-sided limit as well, and so we should be approaching from the left-hand side in that case. So we're approaching from that side of -5. So when we go to the graph, we get down towards this point. So what is the y value that we're approaching? Well, our y value, if you notice, if we cross that over here, that y value looks like it's -2. Okay, so in fact, our limit as x approaches -5 from the left would be -2. Okay, so we have a left-hand limit and we have a right-hand limit. And so what we have is a theorem: if limit as x approaches, let's say some c of f of x exists, then you need the left-hand limit, so limit as x approaches c from the left of f of x, to equal the right-hand limit, and they equal some number which we'll call L, right? In this case though, notice our numbers are different. So that means for this scenario, since our left and right-hand limit are not the same, this is a does not exist scenario. Okay? So now what people do is they kind of confuse the idea of limits with function values. So this is actually a college algebra question, but we'll toss it in here too. F of -5. So notice when we go to x equals -5, we have this dot right here. And what's the coordinates of that point? Because that's what lies on the curve. This is -5, and the y value is 1. So this value right there, that is f of -5. So at the end of the day, we get 1 for our answer right there. And in a similar manner, we can go back to that value where we found f of -2. That value is -2, and then notice if we cross that over, that's going to be -3. Sitting right there. And so this -3 would correspond to f of -2. So that is equal to -3. So now, last but not least, let's go over to limit as x approaches 5. So what has to happen? Well, we need to look at the left-hand limit, and we need to look at the right-hand limit. So notice our left-hand limit looks like it's approaching 7 versus our right-hand limit in this case would be approaching 3. So since those two values aren't equal, we have another does not exist scenario. Okay? So keep that in mind. We need the left and right hand limit to be equal in order for this limit to be the same. Kind of what happened in the case of limit as x approaches -2. Our left and right hand limits were both 2, so we ended up getting our answer to be 2 in that case. Actually, in this case right here, our last one, as we approach 5, and then also -5, we actually have what's called a jump discontinuity. So something to keep in mind for later down the road. Alright, so now let's actually get into calculating these limits when we have cases of functions listed there, or things that or expressions or whatnot, and how will we actually solve those. So there's a multitude of ways, and we're going to try and touch on quite a few of them. So we have the limit as x approaches 5 of x squared minus 7x plus 10 all over x cubed minus 125. So in that case, what actually happens is we first plug in, and when you plug in the numerator you get 5 squared minus 7 times 5, so that's going to be -10 plus 10 is 0, and then in the denominator you get 5 cubed minus 125. That tells us that we get 125 minus 125, which is 0. So since we got 0 in both of those cases, and they're both polynomials, that's important. Since they're both polynomials and we both got 0, we actually know something. We know that x minus 5 has to be a factor of both terms. So since x minus 5 is a factor of both terms, we can write down the rest of this. X minus 5 times what would give us x squared minus 7x plus 10. Well, we need to make a -5 times what will give us plus 10. Well, it has to be -2. So you get x minus 5 and then an x minus 2 sitting there. In the second case, notice we need x times something to give us x cubed. Well, that'll be an x squared. This is actually a difference of cubes, by the way, and because 125 is 5 cubed. So if you know the formula, it becomes quite easy. If not, that's okay. We can still work it out. So what we'll do is, if we put a 25 is what we're going to need on the end, because -5 times 25 gives us -125. But in that case, we'll need a 5 in the middle, because you'll get the -25x will cancel off with the 25x. So right there. And then we have the x squared term, so you get -5x squared here, and then you'll get +5x squared there, which cancel off as well. So that's what the difference of cubes is doing. But notice now what that allows us to do is we can cross off those x minus 5 factors, and we're left with this limit as x approaches 5 of x minus 2 over x squared plus 5x plus 25. And so what does that make? Well, we just plug it in, and so we get 5 minus 2 over 5 squared plus 5 times 5 plus 25. And so that equals, we'll have 3 on top, and then notice we'll have 25 plus 25 plus 25, that's going to be 75. And so, or 3 times 25, so we can reduce this to 1 over 25, and that's our final answer. Okay, as always, if there's any questions along the way, please let me know. Don't hesitate to ask. That's what I'm here for. So please ask away. In our next case, when we plug in 3, you get 9 minus 9, so you get 0 on top, and you get square root of 3 minus square root of 3. So you might be saying, well, x minus 3 is a factor. Well, yes and no. Notice we have square roots in the bottom. So we're going to have to play with that a little bit. And the way we can deal with square roots is to multiply by what's called a conjugate. And so what does that conjugate look like? Well, the conjugate of this denominator will be square root of x plus square root of 3. Now I can't just multiply willy-nilly where we want. We have to always multiply. If we're doing something to the denominator, we have to do it to the numerator. So that's exactly what's happening right there. So we get the limit as x approaches 3 of x squared minus 9 all over, well, we'll have this extra square root of x plus square root of 3. And then the denominator becomes x minus 3. And notice I haven't done anything to the numerator yet. I could have done it in that first step, but x squared minus 9 can factor nicely. And the way we can factor it now, as we mentioned before, we should have a factor of x minus 3 sitting there. And we did. We just had to conjugate the denominator. So the numerator becomes x minus 3, x plus 3, and then the square root of x, oops, I forgot the square root of 3 there. square root of x plus the square root of 3 all over x minus 3. So notice our x minus 3's cancel, and what we're left with in this case of conjugation, we have the limit as x approaches 3 of x plus 3 times the square root of x plus the square root of 3. So notice this equals, so 3 plus 3, that's going to be 6. And square root of 3 plus the square root of 3, after plugging that in. Oh, let me write down real quick. For the first few, I'll actually write out the extra steps. So you get 3 plus 3 times the square root of 3 plus the square root of 3. So notice that makes 6 times 2 times the square root of 3, which is the same thing as 12 times the square root of 3. And that's our final answer. Okay, so I don't see any questions thus far, so let's keep on moving forward. Oh, we have limit as, and I put theta, let me fix that real quick. Limit as x approaches 0 of tan of 5x divided by 7x. So this is a trig limit, and the way to deal with that, well, you can find tangent of 0 is 0, and 7 times 0 is 0. So the main limit that we're going to need to use, you have a limit where limit as theta approaches 0 of sine of theta over theta, that always equals 1. Now that means if we have theta, if we change it, notice we have a 5x in this case, that would mean we need a 5x down below. But we have a tangent, so what we'll need to do is rewrite this thing. This is the limit as x approaches 0 of sine of 5x over cosine of 5x all over 7x. So that's not perfect, but it can do the trick for us. So this thing equals, we can break up limits since these are, we have a continuous function in the numerator and a continuous function in the denominator. We can kind of break up this limit how we want. So what we'll do is let's break it up into two limits. 1 over cosine of 5x, and that's coming from that up top. And then we can write the other piece as sine of 5x over 7x. Now to make this perfect, we want, notice we want sine of theta over theta. Well, that's not quite there. So what we can do is if we multiply the denominator by 5, we can do the same in the numerator and be in pretty good shape. And so what does that do for us? Well, we write this. The first part we can evaluate. So we'll go 1 over cosine of 5 times 0. And let's see what happens with that. Times, now I'll do a quick trick in terms of that second one. We're going to move this 5 out into the front of the limit along with this 7. Okay, so times 5/7 times the limit. So we'll still have that limit in there. X approaching 0 of sine of 5x over 5x. So notice that's more in the form of sine of theta over theta now, because we have both the 5x in the numerator and the denominator is approaching 0. And so this whole thing, so let me kind of highlight that, this whole piece approaches 1. So at the end of the day, what do we have? We have 1 over, well, what's cosine of 0? Well, cosine of 0 is just 1 times 5/7, and then times 1. So our whole answer is just 5 over 7. And that's our final answer. Okay. So let's take a look at our next one. We have x cubed and then this arctangent of 1 over x. Well, notice it seems like we have 0 times, who the heck knows what that second piece is? You have 1 over 0, and that part's even undefined on the inside. So we aren't quite sure how to handle that just yet. There is one thing, though, that can be useful to us. If you don't recall, I'm going to try and make you recall. If you have the function y equals arctangent of x, which is what we have here, you have a top bound and a bottom bound of the function. So it's bounded between pi over 2 and negative pi over 2. So notice if we have some function arctangent of 1 over x, it's still bounded between negative pi over 2 and pi over 2. And that's what we're going to work with here. Because when we plug in, we have multiplication of 0 and something undefined. What the heck does that equal? Okay, sometimes it works out nicely, sometimes it doesn't. So what we'll do first is we'll bound a function. And what we're going to try and do, and I'll put less than or equal to, even though it doesn't ever quite equal, it still will do the trick for us. So far so good in terms of we have the bounds, right? Now moving forward from here, let's try and write this a different way. Negative pi over 2 x cubed is less than or equal to pi over 2 not pi over 2, I'm sorry, x cubed or tangent of 1 over x, and then that's less than or equal to pi over 2 x cubed. And then I should say this is what happens when x is greater than 0, and then when x is less than 0, you have negative pi over 2 x cubed. This flips the inequality, right? Oops, sorry, wrong way. Now you might be asking, why does it do that? Well, notice x cubed would be a negative, right, in those cases. So there's a way to fix this, and we can have it where it's all one case rather than having to break up into when x is greater than 0 and when x is less than or equal to 0. The simple fix comes right here. What we'll do is we'll drop that, and I'll put it in pink just to see that. We'll put an absolute value around that x cubed, and we'll put an absolute value around this x cubed. So notice that won't make a difference. Worst case scenario, that's as far down as this can go in terms of negative pi times over 2 times the absolute value of x cubed, because that'll turn to a positive number there. So we always have a negative on this outer end, and on the right hand side we'll always have a positive on that end. So we don't have to worry about these cases as long as we put absolute value. Now if I had something like an x to the 4th or an x to some even power, I wouldn't have to do these extra cases, but there's an easy way to fix this. Now why are we doing this? What happens here? Well, the big picture of what happens is we can now take the limit as x approaches 0 of each term. So we have limit as x approaches 0 of negative pi over 2 times the absolute value of x cubed. That's less than or equal to the limit as x approaches 0 of x cubed arctangent of 1 over x. And that's less than or equal to limit as x approaches 0 of pi over 2 times the absolute value of x cubed. Well, if you plug in 0 into this left-hand limit, notice you get 0 times negative pi over 2, which is 0. And on the right-hand side, you get 0. So our limit has to be between 0 and 0. So that means we only have one solution possible. Limit as x approaches 0 of x cubed arctangent of x equals 0. And why is that? Well, it's by what we used here is the squeeze theorem. We basically squeeze this between a value of the function, and the key was that arctangent of x function was bounded. You can use the same ideas in sines and cosines and things like that. So sines bounded by negative 1 to 1, same thing with cosine. Any function that's bounded we can work with and kind of do the same song and dance. So hopefully that makes sense there. Alright, so moving forward, how do we approach these type of problems? So we have infinite limits, and we'll approach one from positive infinity, one from negative infinity. I'm actually going to work backward. I'm going to start with number 6 and then kind of work to what's happening with number 5. Really the idea here is we're going to be looking for the degree. And the degree of, if you look at, you can do the degree of the numerator But what I'd recommend to make your life a little bit easier, always work with just the degree of the denominator. Whatever that might be, that's going to be your multiplier essentially. And what do I mean by multiplier? So our degree of our denominator is x squared. So we can multiply this thing by 1 over x squared, and then the numerator also by 1 over x squared. And why would we want to do that? Well, we're going to take and make good use of one of the properties of these limits, and that's the limit as x approaches infinity of some constant over some variable. Like, so we had x approaching infinity, x approaching negative infinity, we had a constant over some x to some power. What will happen all of a sudden is that that will approach 0 if you just have that constant there, and we're going to take full advantage of that. So in the numerator, notice what we have. Well, when we simplify 15x, so we have to take this times each term, if you recall. So what happens? 15x cubed over x squared, that just makes 15x. And so then we have minus 7 right there, because the x squareds would cancel. And then plus, you'd have 3x over x squared, so that makes it 3 over x. And then minus 4 over x squared up in the numerator. And then down in the denominator, what do we have happen? Well, we have negative 4. Okay. And then we have minus 7 over x. And then plus 8 over x squared. So where do we go from here? Well, when you take a look, this part goes to 0. This part goes to 0, just by what I mentioned before. You have some really large number. In every case is approaching 0. So now, what we're left with is, notice this is negative infinity, essentially, when we go 15 times negative infinity. So that'll be negative infinity. Minus 7, that's still going to be negative infinity up top. But when we divide by a negative 4, negative divided by a negative makes a positive. So that means this whole thing just became positive infinity. That's all there is to it. And so really all we're doing is we're kind of checking what are those coefficients in the lead there. And so the behavior of this, anytime you can kind of just actually not worry about anything else other than the degree of the polynomials. So you could have written this as 15x cubed essentially over negative 4x squared. And it'll take on that behavior. If we wanted to get a little bit more specific, we could get into divide and find the slant asymptote that it's approaching. But this gives you the general idea as to what's happening in terms of the end behavior or the limit behavior. So there is no horizontal asymptote in this case. That's what it's saying. So no horizontal asymptote. And then we approach infinity. In our second case, so as I said, we might want to deal with the denominator. So in this case, what's the degree? Well, you have a square there, but we're taking a square root. And the square root of x squared is the absolute value of x, right? So what we'll do is, in this case, before I write the equal, we'll multiply by 1 over the absolute value of x, and then 1 over the absolute value of x. And since this is positive infinity, that'll just be the same as 1 over x. Okay, so we don't have to worry about the absolute value coming into play where we'd have to do a little trick there. It does get to be a little bit different if you're approaching negative infinity, but since it's positive infinity, we're going to be in pretty good shape. So in the first case, what will we need to do in order to kind of tackle this? Well, when we have the cube root, we have the 8x cubed plus 7x minus 3. Now remember, we said we can drop the absolute value since we're approaching positive infinity. So when we multiply this, so I can't just take that on end just yet. So what we'll do is we'll take a cube root, and then we'll go 1 over x cubed. Because notice when I take a cube root of 1 over x cubed, that's just 1 over x. So we're in pretty good shape there. And in a similar manner, we'll take the square root of 25x squared minus 19x plus 9, and that would be same thing. We have to take a square root and square it. So the square root, and then we have 1 over x squared. Now we can multiply this thing on through. So we get the limit as x approaches infinity of, well, we'll have the cube root, 8x cubed, now remember we have to distribute that to each term. 8x cubed times 1 over x cubed just gives us 8. The x cubes cancel. 7x divided by x cubed, that's going to be 7 over x squared. And then minus 3 over x cubed will be our last term there. And so from there we have in the denominator square root of 25 x squared times 1 over x squared. That'll just be 25. So then minus 19x over x squared, that's going to be 19 over x. And then plus 9 times 1 over x squared, that's going to be 9 over x squared. And so with all that, what happens? Well, you get this piece goes to 0, and this piece goes to 0. It's by properties of a constant over some variable as x approaches infinity, and that goes to 0. So what are we left with? So when we plug this in, we get the cube root of 8 divided by the square root of 25. The cube root of 8 is 2. The square root of 25 is 5, and so there is our final answer. Okay, I don't see any questions on that, so I'm going to continue to move forward until I see something pop up. So next one we have limit as h approaches 0 of e to the 5 plus h minus e to the 5th all over h. How the heck do we approach this thing? So this is going to take a little bit of notice as to what's happening. In this case, what we're going to do, notice you have something like a 5 plus h up here, and this is just the constant. So if I let f of x equal e to the x, right? What happens? Well, we know that in that case f prime of x equals limit as h approaches 0 of f of x plus h minus f of x all over h, right? And if we wanted to look at, say, f prime of x, well, actually, let's do it this way. Let's look at f of x plus h real quick. Notice that would be e, and then our x is up in that exponent, so that would be e to the x plus h power. Okay, so this thing would be e, limit as h approaches 0 of e to the x plus h minus e to the x all over h. Now, there's a caveat here. If you plugged in, right, say f prime of 5, that should be the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h, which is the same thing as what we saw up above. That's the limit as h approaches 0 of e to the 5 plus h minus e to the 5th power all over h. So notice, this is going to be the cool thing, is we can start to calculate certain limits with using derivatives. So f of x equals e to the x. What does that mean? Well, we know the derivative of e to the x is just e to the x. So in this case, this thing, well, f prime of x should equal e to the x, right? And so that means that this second case should just be e to the 5th, and that is our final answer. Okay, kind of cool. Another way you could approach it, you could actually factor out this is e to the 5th and then e to the h. Some of you might recognize, if you looked at the proof of this, you have e to the 5th, e to the h minus 1, oops, e to the h minus 1 all over h. And then a lot of you will know that this, actually, as h goes to 0, this thing approaches 1. Okay, and that came from the proof of why the derivative of e to the x is e to the x. So in our last one, we have limit as x approaches 7 from the left of absolute value of x minus 7 all over x minus 7. This one's kind of tricky in some regards because we have this absolute value sitting here. So first off, if f of x, let me write it this other way, if that equals the absolute value of x minus 7 over x minus 7, anytime you see an absolute value, that's a piecewise function. Okay, so what happens is, in this case where we've broken things off, usually absolute value of x is broken off at 0, so we've shifted 7 units. And notice we can't equal 7 because the denominator would equal 0. So what we'll have is x greater than 7 and x less than 7. Well, if x is greater than 7, you have a positive number for that absolute value. So that's just x minus 7 over x minus 7. And in the other case where you have a negative value, what we've done is we switched that negative, and so you get negative x minus 7 all over x minus 7. Okay? So when we want limit as x approaches 7 from the left, which one are we dealing with here? Well, that should be equal to the limit as x approaches 7 from the left of, well, which scenario is it? Well, it should be when we're less than. And so there's if statements here too. So that should be negative x minus 7 all over x minus 7. And so notice your x minus 7's cancel. And so this is equal to the limit as x approaches 7 from the left. I know this looks kind of weird, but it would just be negative 1 because of that negative symbol out in front. And so that limit must be negative 1. And that, in fact, is our answer. Now, what happened graphically? Well, if you want to draw the graph of this thing, oops. So say we went to the point 7 somewhere. And let's say, I'm not saying this is to scale whatsoever, but say this is 1 and negative 1. Here's what happens with your graph. At 7, if we're greater than that, we're going to be positive 1. And if we're less than that, we're going to be negative 1. And that's how our whole graph looks. So we can draw out the whole thing, everything's good to go. So hopefully that makes sense there. Let's keep on moving forward into derivatives, kind of seeing what happens with the derivatives. And then we'll kind of jump back to some stuff that ties back into limits. And once again, if you have any questions, let me know. I'm here to help. So in this case, find the derivative of the following functions. We have 4x cubed e to the x, or times e to the x. So in this case, we're going to need to use the product rule. So when we take the derivative, we can pull the 4 out front, and then we need to use that product rule. So it goes derivative of the first function times the second function plus the first function times the derivative of the second function. And so derivative of that first function, recall that we have to use the power rule, so that goes 3x to the 3 minus 1, or 3x squared. And the derivative of e to the x is just e to the x, so this whole derivative equals 4 times 3x squared e to the x plus x cubed e to the x. And that can be your final answer. That's more than fine. If you want to get fancy with it, you could probably factor out a 4x squared e to the x. And what are we left with? We're left with a 3 in the first case plus x, I believe. Yep. And you're done. In our second case, we have g of theta equals sine of theta cubed, or sine cubed theta, which I will actually write as sine of theta cubed. And hopefully that allows you to see that we are going to use the chain rule here. And in order to use the chain rule, you need to use that power rule first. So that becomes 3 sine of theta, the quantity raised to the 3 minus 1 power, which is 3 sine of theta squared, just using the power rule. But then we have to take the derivative with respect to theta of that interior function. So we have to take the derivative with respect to theta of sine of theta. And the derivative of sine of theta is cosine of theta. Okay? So this thing becomes 3 sine squared theta cosine theta, and you are done. Okay, moving forward, some other rules that we're going to need to use. Another way to write this one, just to make your life a little easier, we can write this as 5y minus 7 tangent y all over y squared plus 4, and what might look a little better for y'all is y to the 1/2 power. So that way when we calculate h prime of y, we need to use the quotient rule. So you square the denominator, y squared plus 4. I could write y to the 1/2, or I'll just keep it as square root of y for now, but that's squared. That doesn't make any changes. But now we write that denominator again, which I'll write as 4 square root of y, times the derivative of the numerator, so times the derivative dy of 5y minus tan y, and then minus, we're going to write the numerator 5y minus tan y, and times the derivative, and here's where we might want to write that as 4y to the 1/2. Okay. So now let's work it out. 5y, that's 5y to the first power. You can bring the first power, you'll have y to the 0, which is just 1. So 5 is what that derivative is, minus derivative of tangent is secant squared y. Okay. Y squared, that derivative, use the power rule once again, you get 2y. And in this other case, when we bring the 1/2 down, you'll get 2, because 4 times 1/2 gives you 2. And then you get y to the 1/2 minus 1, which is negative 1/2. Okay, so now we want to write all that up. Alright, so h prime of y equals, we'll have y squared plus 4 square root of y times 5 minus secant squared y minus 5y minus tangent y times the derivative, which is 2y minus 2y to the negative 1/2. Another way for us to write that is 2 over the square root of y. Okay. And where do we go from here? Well, all we need is down below, we need that y squared plus 4 square root of y, the quantity square, and you're done. Okay, so now on our q of x, moving forward to that part, we can do a similar thing. You can write this as 5 times x to the negative 1 minus 7, and then this is the arctangent of x, which you may or may not remember. Let me know if you don't remember it. I'll be happy to show you what that derivative is. So using that constant rule, this becomes 5, and this should be negative 1x to negative 1 minus 1. And so then we have minus 7, and the derivative of arctangent is 1 over 1 plus x squared. Are there any questions on that? Okay, so brushing this up just slightly, you can make this negative 5, that's x to the negative 2, essentially. So that's negative 5 over x squared minus 7 divided by 1 or divided by 1 plus x squared. Okay, and that is your final answer for this one. So I don't see any questions on the arctangent, how it was calculated. So I'll keep on plugging along. Let's see what we come up with now. So r of x equals secant of natural log of x squared plus 1. So this is a chain rule one. And when you take a look, you get r prime of x equals. So the derivative of secant is secant, usually secant of x, tangent of x, but now instead of secant of x and tangent of x, you have secant of natural log of x squared plus 1, and then tangent of natural log of x squared plus 1. But this is a chain rule because we don't have x in there anymore. We have something a little more complicated. So we need to take the derivative with respect to x of natural log of x squared plus 1. So now moving forward from there, what's the derivative of that? Well, we have the derivative of that should be 1 over x squared plus 1 times the derivative of the anterior function, so times the derivative of x squared plus 1. And then what's the derivative of that? Well, that should be, we should have 1 over x squared plus 1 times derivative of x squared is 2x, and then derivative of 1 is 0, so we just have 2x. So we can actually write out our r prime of x. We get secant of natural log of x squared plus 1, okay, times the tangent of the natural log of x squared plus 1 times, we just found that derivative, it's going to be 1 over x squared plus 1 times 2x, so I'll just put the 2x up top there. And that is a final answer. Okay, moving forward, we can kind of extend the power rule. If you take the derivative with respect to x of f times g times h, that should be f prime gh plus f g prime h plus f g h prime. And why do I mention that? Well, notice we have a product of 3 functions. Okay, so that means that when we take t prime of x in this case, we get the derivative with respect to x of x times sine of x cosine x, which, by the way, we could shorten this up tremendously if you're comfortable with the chain rule. Sine of x cosine x is just 1/2 sine of 2x, so that's just a trig identity we're pulling, but I'm going to avoid the trig identity for now. But if you want to use a trig identity, it will cut down your time quite a bit. So next one, we have x times the derivative of sine of x times cosine x, and then plus x times sine of x times the derivative of cosine x. Alright, so what this gives us is sine of x cosine x plus x times derivative of sine is cosine, so we have cosine x plus x times sine, derivative of cosine is negative sine. Okay, and so then this, you can simplify this just a little bit. You could write this as sine x cosine x. You can factor out, oops, didn't mean an equals, I meant a plus. You can factor out an x of that last bit, and you're left with cosine squared x minus sine squared x. Okay, so moving forward, now we have a nastier chain rule going on here. We have z of x equals this cube root of 3x plus the square root of 5x squared plus 7 plus 9. So this thing equals, another way to write this is 3x plus e to the 5x squared plus 7 plus 9 raised to the 1/2, and then that whole thing is raised to the 1/3. So that means when we take the derivative of this thing, we can just use the power rule to start, but we will need to use the chain rule. So you get 1/3, and then it goes 3x plus e to the 5x squared plus 7 plus 9 raised to the 1/2, but then this is to the 1/3 minus 1, which is negative 2/3, by the way, and then times the derivative of the inside. So it's going to be 3x plus e to the 5x squared plus 7 plus 9 raised to the 1/2. So notice, breaking this down a little bit, derivative of this first part is 3 plus the second part. We're going to need to use that chain rule again, and we'll pull the 1/2 out in front. So 1/2, and then it goes e to the 5x squared plus 7 plus 9 raised to the 1/2 minus 1 in power. But then all that is times, and so remember, it's all this is in parentheses, all that is times, just the last piece though, not the whole thing, is times the derivative of e to the 5x squared plus 7 plus 9. So notice the derivative of the plus 9 part is just going to be 0. So what we're left with is just e to the 5x squared plus 7 times that derivative of the exponent. So derivative of 5x squared plus 7. So this is a lot of work, it seems like. But we can finally, if we recognize that that's going to just be 10x, we can recognize that we can solve this thing. So this is 1/3 3x plus e to the 5x squared plus 7 plus 9 raised to the 1/2 raised to the negative 2/3, which means it's a cube root squared that should appear in the denominator, essentially with the 3. Okay, and moving forward from there, we got to go to our next term, which the derivative started with this, and then it kind of went down and down and down, right? So we have 3 plus, and then notice we have 1/2 to the e 5x squared plus 7 plus 9 raised to the negative 1/2 times, we had once again e to the 5x squared plus 7. And notice this is only times this last term, not the 3. And that is times 10x. So we close off that, and then we can close off our parentheses, and that would be our final answer. Any questions on that one? Okay, I don't see any questions, so let's move on to the next one. What makes this so difficult? You can't use the power rule. You got an x up in the exponent, and then you got an x in the base, so we have to use what's called logarithmic differentiation. And so what we do is we begin by taking a logarithm. It doesn't have to be a natural log, but that'll just be your easiest in terms of derivatives, both sides. That allows us to bring down the exponent. So cosine x, natural log x. And so now what that allows us to do is we can take a derivative of both parts with respect to x. And so this ties into the implicit differentiation stuff that you've probably been dealing with. Because the derivative of natural log of y is 1 over y times y prime, versus the derivative of the right hand side, we need to use the product rule, so this becomes the derivative of cosecant x times natural log of x plus cosecant x times the derivative of natural log of x. Oops, there we go. Okay, so now moving forward, notice we have 1 over y times y prime equals derivative of cosecant x is negative cosecant x cotangent x times the natural log of x. And on the other side we have plus a cosecant x, so the other term I should say, times 1 over x. Now you might be asking, where do we go from here? Well, there's a simple way to solve. We want to solve for y prime. So what we do is we'll multiply both sides by y, but make sure I put the whole other side in parentheses. So I'm multiplying both sides by y. Well, what is y? So I'll write all this. So we get negative cosecant of x, cotangent x, natural log x, plus cosecant x times 1 over x, or you can write that as cosecant x over x, times y, if you recall, is just x cosecant x. And so that's all we're going to do is just rewrite that, x cosecant x, and we have our solution, right? That's the beautiful result. We just multiply by that original function and we are good to go. Okay, so now if you get real good with the logarithmic differentiation, if you understand how that stuff works, you can actually cut down your time drastically, and that's what I'm going to try and show you here. If you have p of x equals this nasty looking function, notice we have a product of 3 functions up in the numerator, product of 3 functions down in the denominator. We're going to have to use quotient rule and the product rule of 3 functions, so it's just going to be all sorts of awful, right? But there's a fix to that. And what we can do is, first off, we can take a natural log of both sides. So natural log of p of x equals, because essentially this is like a y, and then we have natural log of all that junk, x cubed sine x, natural log x, all over e to the 5x, arc sine of x, x cubed minus 4x, and then we close that thing off. So what's so special about this? Well, we can get ready to take the derivative, right? So I'll put d dx of natural log of p of x. which is a function in terms of y essentially, so I'm going to have to use logarithmic differentiation and use the implicit differentiation. But when we do the right hand side, let's simplify things for us. There's laws of logarithms, so everything in the numerator can just be kind of added across with a single logarithm. So we get natural log of x cubed plus natural log of sine of x plus our natural log of the natural log of x. I know that sounds kind of tricky, but it's not going to be too bad. Now everything in the denominator is going to have a minus in front of it. So minus natural log of e to the 5x. And then minus natural log of arc sine of x. And then minus natural log of x cubed minus 4x. And so, oops, I'm going to switch this up just real quick. So there's some simplifying we can do. We can rewrite the first one as 3 natural log of x. Well, that's easy now. And natural log of e to the 5x, that's just going to be 5x. So now when we take our derivative, our life is going to be real good. So what happens is, this is 1 over p of x times p prime of x, right, for the implicit differentiation. And then on the right hand side, derivative of the first one, we have 3 times 1 over x. Now we'll start moving a little bit faster, because basically you put the derivative, if I have the natural log of say some f of x, and I want to take this derivative, right? How do we do that? Well, all you need to do is you go 1 over f of x and then you multiply by f prime of x, but an easier way for us to write that is f prime of x over f of x. So if you have sine of x, the sine of x appears in the denominator, and the derivative of sine of x, which is cosine of x, appears in the numerator. That's just cotangent of x, by the way. Same thing applies here. So you get natural log of x, and notice you have a 1 over x up top. So you can rewrite this as 1 over x natural log of x, with the x natural log of x appearing in the denominator. The next one, derivative of 5x is just 5. The next one, we have arc sine of x. And please let me know if you have questions on how to take that derivative, but this should be 1 over the square root of 1 minus x squared, I believe. And then the last one, we have x cubed minus 4x appear in the denominator, and then the numerator should be 3x squared minus 4, just by using the power rule. Okay, I'm going to, well, I should use parentheses here. So what do we do on this? Well, if we multiply both sides of our equation by p of x, notice our p of x is on the left hand side would cancel, and we're left with exactly what we want on the right hand side. So p prime of x equals, let's brush this up just slightly. So you get 3 over x plus cosine of x over sine of x is this cotangent of x, plus our next one is 1 over x natural log of x minus 5 minus, we can move that square root of 1 minus x squared down below. So we get 1 over the square root of 1 minus x squared times arc sine of x down in the denominator minus, we can't do any factoring there, it seems like, so we just left with 3x squared minus 4 over x cubed minus 4x. And then all that's times p of x. Well, p of x, if you recall, we go up back to the top. That is just x cubed sine x natural log of x all over e to the 5x arc sine of x. And then it's x cubed minus 4x. So I bet if you try to do it the other way, you'll still be working, and you'll probably run out of space. That's the big thing, is because you have that product rule and product rules, so you have a ton of different terms if you're to try and do it that way. I'm not saying it can't be done, it's going to take up a lot more time. So hopefully that makes sense on the logarithmic differentiation. So now let's get to some applications and things like that. So you've seen limits, seen derivatives. How can we start to apply this thing? Well, first off, continuity. How do we know a function is continuous on on a whole interval? Well, you look for problem points, and in this case there's only one problem point that can occur. It's 3. So in order for this to occur, so we need the limit as x approaches 3 of f of x exists if, first off, we need the limit as x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right of f of x, and f is continuous at c, or at x equals 3 in this case, if the limit as x approaches 3 of f of x equals f of 3. So in this case, we need the left hand and right hand limit to basically line up. So what we'll do is we'll take the limit as x approaches 3 from the left of f of x and set it equal to the limit as x approaches 3 from the right, since that's the only problem point that we're dealing with here. So what does that mean? Well, that means the limit as x approaches 3 from the left, well, that should be 3 from the left would be when we're smaller than 3, cx squared plus cx equals limit as x approaches 3 from the right of, and then that function would have to be the bottom function because x would have to be greater than or equal to 3. And so we're left with c squared x. So what happens to this equation? Well, you can plug in 3's in for the x, and so notice that becomes c times 3 squared plus c times 3 equals c squared times 3. Which is, if you simplify, you have 9c plus another 3c, that makes 12c equals 3c squared. Get all your terms over to one side, so you get 0 equals 3c squared minus 12c. Get 0 equals, you can factor out a 3c in that case, so you get a 3c, and then what are we left with? We're left with a c and then a minus 4. So that means c equals, we set each factor equal to 0, so you get c, the 3c equals 0, that meaning c equals 0, and c minus 4 equals 0 means c equals 4. And that's our final answer. So we found where it's continuous just by having those two values, and that's it. Okay, moving forward to the intermediate value theorem. Okay, so this one might not seem like an intermediate value theorem. What does an intermediate value theorem state? Basically, if you have a continuous function over a given interval, you can start to see if certain values are taking place by just looking at the function values of that interval, and everything in between is going to get hit, essentially. So let's see how we can actually approach this, and to kind of give you an idea of the intermediate value theorem. So let's say you have some interval, let's say here's a, and now it doesn't have to necessarily be increasing or decreasing. I could have something that goes up here, down below, and finishes right there at b. But you have some f of a value, and then you have some f of b value, and then there's a range, essentially. Everything in between these two pink bars has a value inside of this interval that's going to hit here. We don't know exactly where, but we just know it happens. Right? That's all. And the only reason that we're using that is it's a continuous function. So that's what we're going to try and apply here, and I'll kind of show you how it works. So does there exist a number that is exactly one more than its cube? So if you look at this, we have, first off, exist a number. Let x be a number. Now, if it were to be exactly one more than its cube, one more than its cube, what does that mean? That's x cubed plus 1, right? So you add 1 to the cube, and what we should have is that should be the same thing as x. Or in other words, so this is kind of nasty to set this up, but if we wanted to kind of see if there's a solution, what we're looking for is x cubed minus x plus 1 equals 0. And I don't have a calculator on me or anything like that, so how the heck do I figure this out, right? So what we do is we can start with a function. So let f of x equal x cubed minus x plus 1. So notice it's a polynomial, so f of x is continuous. We would only need the interval that we're going to work with, but in this case it's continuous on the interval negative infinity to positive infinity. So what we can do is apply the intermediate value theorem. So also, now what we need to do is pick two values such that 0 is in between those two values, those two function values after we plug in. So if let's try f of negative 2. Let's see what pops out. And this might take some practice in terms of kind of gauging where those function values might lie. So notice we get negative 2 cubed minus negative 2 plus 1. So that's going to be negative 8 plus 3 essentially, so that's negative 5. Also that, and then let's check out f of negative 1. I could pick any other value as long as I have something that's positive. Notice 0 would be in between these function values. So what happens when we plug in negative 1? What do we get? We get negative 1 cubed minus a negative 1 plus 1. So that should equal plus 1. So this implies, what does that imply? That 0 is in between f of negative 2 and f of negative 1, right? Because you have negative 5 and 1. So now what we can apply is the intermediate value theorem. Hence, by the intermediate value theorem, there exists a c in which interval? So what is our a and our b? Well, essentially we had negative 2 be our a and negative 1 be our b. So there exists a c in negative 2, negative 1, such that f of c equals 0. So, but if f of c equals 0, hence, or therefore, or whatever you want to write, so this implies, well, notice what was f of x? It's x cubed so this implies the existence of a c such that c cubed minus c plus 1 equals 0, or more simply put, c cubed plus 1 equals c, which is what we wanted in the first place. Okay, so that's another way. It's kind of roundabout, it seems, but we were able to show it. Now notice I didn't find the value. And by the way, you can make your interval larger if you wanted. If you went to negative 5, for example, you could say the interval is negative 5, 0, right? That would work because 0 you get 1 as a function output. And notice you'd have negative 5, 0. There's a solution to this. So somewhere in there, but notice we condensed it a little bit when we went negative 2 to negative 1. That's a pretty small interval, only a unit of 1, versus something real large in terms of our interval where we're trying to guess. And we can try and condense it on down, and get an idea of where this value lies, right? But we know it exists first, and then we can narrow it down further and further if need be. But without a calculator, I'm not so concerned on that. I'm just concerned on can we prove the existence? And then the rest is just kind of condensing these by plugging in numbers closer and closer to it. So hopefully that makes sense on the intermediate value theorem. Are there any questions on that and how it works? The big part, though, I can't emphasize enough. If you don't have continuity, all bets are off. right? Because then I can start jumping around and missing values in between. So that continuity is the most important part. So now, tangent line stuff. Determine the tangent line to the curve x squared plus y squared, that quantity squared, equals 4 times the quantity x squared minus y squared at the point 1, and then this nasty square root of negative 3 plus 2 root 3. Okay, so how are we going to handle this thing? Well, we need to use implicit differentiation. And how do we do that? Well, we just take our derivatives how we normally would. But when we use the power rule on this part, right, this becomes 2 minus 1, which is just 1. But we need to use the chain rule on the inside. And our derivative was with respect to x, so I'll talk about that in just a second. And on our right-hand side, you get 4 times. Here's the tricky part. So you get 2x in that first part, but minus derivative of y squared is going to be 2y. But since we took the derivative with respect to x, there's technically a chain rule sitting there. And so we'll go d dx of y. So same thing applies on this left-hand side. Oh, and you might be asking, I apologize, I got a little ahead of myself. We're talking tangent line. So what do we need to find? We need dy dx, or y prime, however you want to write it. Need dy dx because that's the slope. Okay, so to keep that in mind, that's what we're kind of working with. So when we go from here, we get 2x plus 2y, and then d dx of y equals 4, and then we have notice we can factor out a 2 here. Let's make our lives a little bit easier. 2, and then we get the quantity x minus y. Oops, got a little ahead of myself there. X minus y, but then d dx of y, what is that? Well, that's just dy dx. The derivative of y with respect to x. Okay? So now, let's see here. We have a 2 here and a 2 here. We can factor out a 2, bring it all the way out into the front. So you get 4 times the quantity x squared plus y squared. Times, so since we factored out the 2, we have x plus y dy dx. And that equals 4, or 4 times 2, I should say, so let's make that 8, times x minus y dy dx. Okay, so you can divide the 4 on both sides, and so when you divide both sides by 4, we can get, this becomes just 2, making our lives a little bit easier, and then distribute this x squared plus y squared to both terms, because what we were solving for is dy dx, so we want to get it all on one side. So notice we get x cubed plus x squared y dy dx plus, and notice I have to do the same thing with a y squared as well. So we have xy squared plus y cubed dy dx equals x minus y dy dx. Wowzers, right? We're solving for dy dx though. Get all the dy dx's on one side, everything that doesn't have a dy dx on the other side. And so our life will be easy then. Add y dy dx over to this side, so we have y dy dx. Notice we'll have a plus x squared y dy dx plus a y cubed dy dx equals x. Now we have to subtract off. Let's see what we need to work with. You have that x cubed and then an xy squared. So x minus x cubed minus xy squared. So notice from here we can factor out a dy dx. We get dy dx, and then we can go y plus x squared y plus y cubed. Okay, and all that should equal x minus x cubed y minus xy squared. And so we go right up here. We can finally get our solution for our derivative. Notice we have x minus x cubed minus xy squared. By the way, there are some other routes here. And then you have y plus x squared y plus y cubed. Okay, notice in the denominator we can make our lives a little bit better. Everything has a factor of y in it. So let me factor that out and let's rewrite that denominator just to make lives a little bit easier for us. So we can factor out the y, and then what are we left with? We're left with 1 plus x squared plus y squared. Okay? That'll be a little bit nicer for us. Same thing you can do in the numerator if you want to make your lives a little bit nicer in terms of our derivative. If you factor out an x, you get 1 minus x squared minus y squared. Ooh, so close, right? And then all over you have y. 1 plus x squared plus y squared. Okay. So now at the point 1 and then this nasty square root business, we want to find the slope. So let me kind of mix and match here. So if we have dy dx at the point 1 square root of negative 3 plus 2 root 3. What the heck does this mean? Well, this is the slope of their tangent line. So slope of our tangent line. And so what does this equal? Well, x is 1, so that's easy there. You get 1 minus 1 squared. Okay, that's easy as well. And then minus, this is where it gets a little nasty, negative root 3 plus 2 root 3. And we want to square that quantity. Okay. All of this is divided by y, which is that root negative 3 plus 2 root 3. And in this case, though, we're going to go 1 plus our 1 squared plus our y squared, which is negative, or the square root of negative 3 plus 2 root 3. And then we want to square that quantity. And close it. Wowzers. So this slope of the tangent line, notice what we have happen in the numerator. The square makes our life a little bit easier. You get negative 3 plus 2 root 3 all over. Notice you have a square root of negative 3 plus 2 root 3 down below, and then a 2 plus and then when we square that bit, we'll get negative 3 plus 2 root 3. Okay, so we can't simplify it too much, but we can do something here. This is essentially the same factor as up above, except the factor up above is squared. This was a square root. So at the end of the day, what we have is this becomes the root negative 3 plus 2 root 3 once again, and that will cancel off with the denominator right there, and so you're left with 2 minus 3, which is negative 1. So negative 1 plus 2 root 3. Whew. So that's just for the slope. Now the fun part, right? Well, it's not too hard from here. So your final formula, remember, it goes y minus y1 equals m times the quantity x minus x1. So y minus, what's our y1? Well, our y1 is right there. So it's the square root of negative 3 plus 2 root 3 equals m, which we just found, square root of negative 3. And by the way, I simplified it here. It didn't need to be simplified as much as just understanding that you're plugging in numbers. So we have some simplified formula there, and then it goes x minus, what's our x value? Well, our x value is 1 for our point, and then we're done. So that is our final answer. So granted, it took a little bit of work, but we were able to get there nonetheless. Okay. Any questions on that? I know that's a tricky one, but I wanted you all to see it. So do we have any questions at this point? Okay, no questions then. We'll move forward on to our last problem here. So find a formula, or last two problems I should say. Find a formula for the nth derivative of x if f of x equals x e to the x. So the real trick to this is catching a pattern. So first off, we got to find f prime of x. Well, it's the product rule. So product rule, hopefully you're getting pretty good. You take the derivative of the first function, which is x. So the derivative of first function x is 1. So you get 1 times e to the x plus x times the derivative of the second function. What's the derivative of e to the x? Is just e to the x. Now an easier way, I wouldn't always recommend brushing this up, but an easier way for us to kind of write this down is e to the x, x plus 1. Okay? Or you could write it e to the x, 1 plus x, either way. It works out just fine. So I'll write it as 1 plus x for now. So now our second derivative. What is that? Once again, you got to use the product rule. I'll use the e to the x bit first. Oh, just to make it, no, that's fine. Derivative of e to the x is just e to the x, so you're left with e to the x, 1 plus x. And then plus e to the x times the derivative of this bit. Well, what's the derivative of that bit? Well, it'll just be, if you notice, you have 1 plus, derivative of 1 is 0, and derivative of x is just 1, so it's just 1. So notice we have an e to the x, 1 plus x, so that would make e to the x plus another e to the x. That means you have 2 e to the x's. So this thing is e to the x, and it would be 2 plus x. Third derivative. So we take the derivative of this derivative now. What happens here? Well, same song and dance. Product rule once again. Derivative of the first function is just e to the x, so we're left with e to the x, 2 plus x. And then plus e to the x times derivative of now 2 plus x. Well, derivative of 2 is just 0, and derivative of x is just 1. So now we have 2 e to the x's and another e to the x. That makes 3 e to the x's, so you get e to the x, 3 plus x. And hopefully you can see the trend, right? And if not, that's okay. You just try a few more until you can catch it. But in this case, notice we have an e to the x with every derivative. And then what happens? Well, notice first derivative we had 1 plus x. Second derivative we had 2 plus x. Third derivative we had 3 plus x. Well, the nth derivative, what we'll have is just n plus x. And that's our final answer. Okay. So, and you could check that formula. Check the fourth derivative, make sure it follows that formula. You can double check and triple check and keep on going if need be. So for our next one, find the 107th derivative of x if f of x equals sine of 2x. So the first thing we'll start seeing, and in this case we'll do a little bit of simplifying, but not all the way. So f prime of x, in this case, what's the derivative of that? Well, we get cosine of, notice it would be 2x, but then using the chain rule we got to take the derivative of the inside, so that would be multiplied by 2. Okay? So in other words, we have 2 cosine of 2x. So then the second derivative, right? So what happens there? If you take a look at the derivative of cosine, notice we have 2, and then it would be negative sine of 2x. But then we got to multiply by the derivative of the inside, which is 2 again. So notice that makes 2 squared. And then we'll have a negative symbol out in front. Sine of 2x. Let's see the third derivative. Okay, so now we got to take the derivative of this. So we get negative 2 squared. And then what's the derivative of sine? Well, it's cosine. So you get cosine of 2x. And then times that 2 again. So notice this is negative 2 cubed. Cosine of 2x. So I bet you're starting to catch a trend in terms of what's happening thus far. Hopefully we can finish that trend. So in the next case, we got to take the derivative of cosine of 2x. We already know what that is going to be. That's going to be negative sine of 2x times 2. So notice this makes negative times a negative makes a positive. 2 to the 4th sine of 2x. So notice this kind of cycled back to the sine of 2x. The only thing is we'd have a 2 to the 4th sitting out in front. And you can check and see the fifth derivative. If things go appropriately, we should have a 2 to the 5th. Is what happens. Derivative of sine of x, and the 2 to the 5th comes from, well, actually I'll write it out here. You get 2 to the 4th. Derivative of sine of 2x is cosine of 2x. And then times 2. And so notice that makes 2 to the 5th. Cosine of 2x. So what happened here? What's going on, right? We can try and catch a general trend. But so we've repeated, if you notice, the cosine of 2x and cosine of 2x came back together. If you look at on the fourth derivative, you had sine of 2x and sine of 2x. If we look at the sixth derivative, the negative version will come back in. So you get, when you go 2 to the 5th, you get negative sine of 2x times 2. Notice that makes negative 2 to the 6th sine of 2x. Okay? And so that corresponds more, the negative corresponds to this one. So how do we figure out the 107th? Well, there's part of this that isn't hard at all, right? The part that I say wouldn't be hard at all is the fact of you're going to have a 2 raised to the 107th power. Now, where do we catch that pattern from? Well, notice the first derivative had 2 to the 1st, the second derivative had a 2 squared, the third derivative had a 2 cubed, fourth derivative had a 2 to the 4th, fifth derivative had a 2 to the 5th, sixth derivative had a 2 to the 6th, so you're going to have a 2 to the 107th happening there. Okay? Now, the next part we got to figure out, is it sine or cosine? And I don't think that's too hard either. You have 107, so notice for 1, 3, 5, you had cosine. All of those are odd numbers, and all the evens, second, fourth, sixth, those all had sine. So this one's going to be a cosine of 2x. So it's just alternating between sine and cosine. Now, the real trick is it negative or is it positive? Now, that's a little bit trickier. Notice it goes second, third derivative were negative. Then it would be, if you add 4 to those, right? Because basically it's cycling every 4. So add another 4. You'll get 6th and 7th derivative. Add another 4. You'll get 10th and 11th derivative. Well, the easier way for us to do that is take 4 and divide it into 107. Let's see what remainder we get. So notice we take that into our value here, and so we get a remainder of 3. So what that tells us our behavior is like is somewhat similar to this. Only difference is going to be the 2 cubed. So notice in that case we do have a negative, so our final answer for what that 107th derivative is, these are kind of cycle on through, but you get negative 2 to the 107th power and then cosine of 2x, and that's your final answer. So hopefully the review helped you. I don't see any questions at this point. If there are questions, there's also discussion boards you can post and all that stuff. So I hope you take advantage of all that, and I wish you all the best of luck on that midterm coming up. So hope you all have a good night.